All right, folks, in this video here, we're going to talk about page 59, maximum and minimum of quadratic function number 2. And lots of students have asked me this question, like, Tony, when I analyze the scenarios, right? Especially when there's another variable a in the domain, how do I actually know when to start and how do I start? So I'm going to go through this question one by one, again, with the help of Desmos. This is a very good app for us to understand the graph for a quadratic function. Later on, you can use it for any other graph as well. It's very helpful. And I will show you how. Okay. So first of all, I actually established this graph over here as the same quadratic function here, x minus 5 to the power of 2 plus 3. I also set x equal to 5, so I can see that this line over here is x equal to 5. That's my axis of symmetry, which is also my x coordinate for my vertex. And then I leave my range over here for a smaller or equal to x, smaller or equal to a plus 4. The reason why that I need this is so that I have this little shaded area here, you see, we can move it around for us to understand why and how are we going to evaluate everything, right? So next is that we have the a value, which I can track through it in terms of changing the domain here and there. This is actually very helpful as well. Okay, so now let's take a look at the question itself. We have a given quadratic function fx is equal to x minus 5 to the power of 2 plus 3. And we have a domain for x in between a and a plus 4. Here's the tricky part because we do not know what a is. So that's why we have to analyze and evaluate a, and different minimum and maximum points actually really depends on the value of a as well. But we have to know the specific point of difference. And I'm going to explain the point of difference to you later. Okay, so we're trying to find the maximum and minimum values. So solution here is that the equation of the axis of symmetry, first of all, always find out the axis of symmetry, because the axis of symmetry will allow us to find the absolute maximum or minimum. In this case, because how the graph look like, I will have absolute minimum point because this is concave up, right? So at this particular stage, which is my axis of symmetry, which is also my vertex, I will have my minimum point at when x is equal to 5, y is equal to 3, right? So this is pretty easy for us to find out. Now, let's introduce something that's called the point of indifference. When I see the point of difference, especially for the range, you see the left side range is a, the right side range is a plus 4. So can I find out at what point or at what value of a will I have the same y value? One more time, okay? If I substitute the a into the function here, and I substitute a plus 4 into this function, and I let these two equal, and that's exactly what I'm doing for here. And then if you setting f a is equal to f a plus 4, and I will be able to find out the value of a and a plus 4 when the two equations equals, which means that what I'm trying to find out here is, show you guys this, is when a is equal to 3, that this is, again, from the calculation over here, I will be able to find out these 2 points, right? These 2 points. So you will see that when you substitute a is equal to 3, and when you substitute a plus 4, which is equal to 7 into it, these 2 points should share the same value, which means that at that specific point, when a is equal to 3, I will have the same maximum value. Again, it's based on the equation itself because this equation is concave up, right? All right, so, but at this particular point, my minimum point is still my vertex, which is still 3. So I always want to begin my evaluation or my analysis using the point of indifference, which means that I actually wanted to start with this. This is actually easier for us to understand because when a is equal to 3, my maximum point is going to be equal to 7 when I substitute a equal to 3 and a plus 4, which is 7, into the equation of x minus 5 to the power of 2 plus 3, I'll get 7. And that will always be my maximum, no matter what. However, my minimum point at this point will actually be my local minimum, which is also my absolute minimum. In this case, is equal to 3, according to my vertex, right? Now, let's erase everything now, okay? So once I get my point of indifference, which is my number three step, I wanted to move back. And how do I move back and when do I move back? Is first I have to think, what if my right side extreme of my domain, in this case, in particularly, is going to be a plus 4, is actually on the left side of my vertex or left side of my axis of symmetry. So if I were to use the graph, it's going to be looking like this, okay? So watch the graph moving on this side, okay? So you know this is my axis of symmetry, which is on the x is equal to 5, right? What if my a plus 4 is actually on the left side of it, which means my domain is going to be somewhere over here. Watch this. Watch. So the domain is going to be moving somewhere over here, but a will never be greater than 1, right? Because once it hits 1, guess what happened? The minimum point will actually become the vertex, which is my absolute minimum point as well. So from a left side all the way until A is going to be slightly less than 1 over here. As you can see from the graph here. Oh, slightly. Okay. As you can see from the graph over here, my minimum point is going to be here and my maximum point is going to be here. But my minimum point will never be what? Will never be my vertex, right? So in this case, you just have to use the left side of the domain, which is A, to substitute into the equation of x minus 5 to the power of 2 plus 3, which you will get a squared minus 10a plus 28. So this will be your maximum point. On the right side, however, you substitute a plus 4 into the x minus 5 to the power of 2 plus 3, which this will be your minimum point. But this minimum is very different from the 3. Why? Because as you can see from the graph over here, it's not really touching or it's not really equaling to the local minimum, the minimum point of 3. Okay, so this is when my right side extreme of my domain, which is a plus 4, is less than the 5. X equal to 5, this is my axis of symmetry. So which means that my right side is barely or not even touching the axis of symmetry. So this is actually how we evaluate the first scenario. Now it's the second scenario now. Okay, let's take a look at the second scenario. The second scenario is telling me that when A is in between 1 and 3, and mind you that the reason why here this is actually equal, smaller or equal, okay? Or actually greater or equal to it. But this one is smaller. So watch the graph now, okay? According to what I have from scenario number 8, I already have the 1, okay? So you guys know that we are not really touching it, but what if it touches, what if it touches the 1, right? Watch this and see where the minimum point and maximum point is, okay? As soon as it touches it, you will see that the minimum becomes the vertex. And as it goes along, so the minimum point is always going to be over here as well, right? It's going to be my vertex. But my maximum point, it's still on my left side. And up until the stage where the indifference, which is 3, right? When A is equal to 3, hi, Masa, I will now have the maximum point as A equal to 3. So that's why you cannot let A equal, in this scenario here, you cannot let A equal to 3 because we have already evaluated A equal to 3, which the 2 maximum point over here will be indifferent, right? So my evaluation between this stage is when A is equal to 1, which means that the right side extreme of the domain, the A plus 4, is particularly equal or on the axis of symmetry. Once it moves along, right, as you can see them move along, before it hits A equal to 3, right? So in this range, my minimum point is always going to be the vertex. And my maximum point is where? My maximum point is, so let's see it moves. My maximum point is going to be the left side, right? The maximum point is always going to be the left side, right? If I draw this, you will see that. Oh. I don't need that. Okay, my left side, so this is my extreme, right? This is my maximum point. This is my minimum point, right? And then let's try moving this along again, right? Here, see? This is my minimum point again, but then this is my maximum point. So my maximum point is going to be the left side, which explains my maximum point is on the left side of the domain A, right? So you substitute A into the function over here, you will get A squared minus 10A plus 20A. And your minimum value is always going to be the vertex, which is just when x is equal to 5, and then your y is equal to 3. Okay, now I have already solved A, B, C. Again, I started with C and go back to A and go to B. Now, I have to evaluate from the right side now, right? So before we're talking about when the domain is on the left side, moving from the left side to the right side. Now we're talking about from the left side to the right side, which means that this is the scenario now. What if, right? So remember, we are somewhere over here, right? From my C. Now, if it's the scenario number D is when A is start to be bigger than 3. So watch what happened, right? As you can see that, right? Let me use a number, let's say 3.4 over here, right? If it's 3.4, my graph is going to be covered here. As you can see that the minimum point is still the vertex, but my maximum point, instead of on the left side, now it becomes on the right side. And when does this right side end? The right side ends when A is greater, smaller, or equal to 5, or actually greater or equal to 5. Watch this, okay? Hit the 5, and you can see that the minimum point becomes, right, becomes the vertex. And then once it surpasses it, the minimum point is no longer the vertex, right? So if I were to evaluate that, I will set my left side for my A as 3, which is again the point of indifference, my point of indifference, up until A is equal, smaller or equal to 5. Why is it 5 again? Because once it hits the 5, right, my minimum point is still the vertex. But once it's bigger than 5, which is my scenario number E, my minimum point or my minimum value is no longer the vertex. My minimum value is just the left side of the equation. So one more time for number D, okay? How do I get to 3? This 3 comes from the point of indifference, okay? Similar with the 3 over here. So as you can see that this 3 is the right domain of the A. This 3 is the left domain of the A when we're moving forward to the right side. Where does this 5 come from? This 5 is actually the vertex because we want it to stop at the vertex, right? As you can see one more time, at the vertex. So if in case of A is in between 3 and 5, my minimum point is always going to be the vertex, which is when x equal to 5 substituted in, you will get y equal to 3. My maximum value is going to be the right side of the domain, which is a plus 4 when you substitute a plus 4 in it, right? So this explains the scenario number D. Last but not least is scenario number E. Number E is when A is going to be greater than 5. As you can see that as soon as the A on the left side is greater than 5, the minimum becomes the left side extreme. The right side, the minimum becomes the left side extreme, and the maximum becomes the right side extreme. So that if you go move forward with that, you would always see that, right? The minimum is here, all right? And the maximum is here. Okay, so hopefully this video helps you guys understand page 59, maximum, minimum. Again, when you use different quadratic functions, in this case, it's concave up, right? So you can evaluate this way. But I believe 60, right? I believe in the 59B. Yeah, there we go. 59B, we're talking about the concave down. So very similar to it, but it's the same idea that how you have to think of the domain of X and starting from the middle, which is the point of indifference, and then starting from the left side to the right side, or from the left side to the right side. Okay, so this helps you understand the maximum minimum idea. Okay. All right, so if you guys have any questions, leave a comment below, and then I'll see if I can explain more. Okay, thank you.